Today, my talk is going to be about a recent paper with Xavier Tolsa on the regularity problem for the Laplace equation in rough domains. So let me start. I was hoping to start. Yeah. Okay, now it starts. So you have probably seen this several times by now, but we say that a set E is n alphas regular if it is closed and it satisfies this condition for the n Hausdorff measure. So in this talk, we will be dealing with just boundary domains, that they are so open and connected so that their boundaries are n alphas regular. We'll denote the surface measure as, by sigma, and it's going to be the restriction of the n Hausdorff measure to the boundary. And let us recall what the continuous Dirichlet problem is. So we say that if we have a boundary function f, then U is a solution of the Dirichlet problem. If it is harmonic inside the domain, U is continuous all the way to the boundary and agrees with F on the boundary. So this is just to remind ourselves. But then we're interested also what happens like in the case of non-continuous data. So let us introduce also what the notion of LP solvability of the Dirichlet n-regularity problem. So first we will need some notation, and we will define gamma alpha of x to be the cone with vertex x and aperture alpha to be just like defined as usual, like this set gamma alpha. And then we define the non-tangential maximal function u of u to be exactly this particular operator, which is just we take the supreme over all the points in this cone of absolute value of u of y. So, okay. Then we'll say that the Dirichlet problem is solvable in P for the Laplacian if, okay, like I mean, we'll need to start from some known data. So we'll start with continuous data. So if for any f, which is continuous at the boundary, the solution of the Dirichlet problem, of the continuous Dirichlet problem, satisfies also this non-tangential estimate, this quantitative estimate. And then we'll also say that the regularity problem is solvable in LP for the Laplacian if for any f, which is Lipschitz on the boundary, the solution of the Dirichlet problem, the continuous Dirichlet problem with boundary data f satisfies this non-tangential estimate, but now it is for the gradient. So you see, like, I mean, it is pretty clear that in the Dirichlet problem we have like data smoothness 0, let's say, while here we have smoothness 1. So we start with Lipschitz data, and then we ask for a non-tangential estimate of the gradient. All right. So this is just a regular problem. So a major question in the field is like, okay, for which domains omega we have that the Dirichlet and the regularity problems for some LP are solvable. So let us start with the solvability of the Dirichlet problem, and we start with with a paper of Dahlberg in 1977, where he showed that in bounded Lipschitz domains, the Dirichlet problem is solvable for any p from 2 minus epsilon to infinity. And then in 1990 now, David and Jerison, and independently Sams, showed that in chord-arc domains, also the Dirichlet problem is solvable for some p, by showing that the harmonic measure actually is infinity. And then in 2010, Hoffman, Mitrea, Taylor, they showed that in epsilon regular Sams Kenig Toro domains, if you fix a p, then in fact you can find an epsilon, so that the Dirichlet problem is solvable for for all epsilon domains, epsilon regular Sams-Kenig Toro domains. And then actually later in 2017, Azam, Hoffman, Martel, Nystrom, and Toro showed that uniform domains with uniform rectifiable boundaries are in fact chord-arc domains. So in fact, we have again solvability of the Dirichlet problem by just the work of the Gerson and Sams. And in semi-uniform domains with uniform rectifiable boundaries, this was solved in 2019 by Jonas Azam. And eventually, in 2020, Azam, Hoffman, Martel, Tolsa, and myself actually gave the characterization of the domains in which the LP Dirichlet problem is solvable. And this is exactly like, or rather, I mean, the corkscrew domain, the domains that they satisfy the corkscrew condition with Alphorst-David regular boundaries. By saying that the Dirichlet problem is solvable if and only if the domain has interior big pieces of chord-arc subdomains. Okay, so far so good. And then let's see, because I mentioned like several properties, uniformity, semi-uniformity, corkscrew domains. Okay, I understand that many of you may not be familiar with this topic, but let me say that here we have like that, of course, as you can understand, Lipschitz is like less general than chord-arc, which is less general than semi-uniform with Alphorst-David regular boundaries, and further less general than the interior big pieces of chord-arc domains, the domains that they satisfy this condition. So, okay, we say that omega is a corkscrew domain if for every x at the boundary and every r of the diameter of the domain, there exists a ball which has comparable radius and is totally contained in omega and of course in the ball Bx rho. So you can understand this as a quantitative openness condition of the domain. And then a domain is called chord-arc if it has Alphorst regular boundary and satisfies the following. First, it is a corkscrew domain. Second, it satisfies the so-called Harnack chain condition that goes back to Kenig and Jensen. And I will not give a definition of this, but consider it as a scaling invariant quantitative connectivity condition between any 2 points in the closure of omega. And we also ask that the complement is big, so it has like a corkscrew domain. It's a corkscrew domain as well. So this is what the chord-arc domains are. For example, if omega satisfies 1 and 2, then it is called uniform. So if you go back to the previous slide, you will see that we used the notion of uniformity. And then if omega satisfies 1 and 3, then we call it two-sided corkscrew domain. All right. Bear with me here. I understand that's quite some information. But then we also need some geometry of the boundary. Well, uniform rectifiability, it goes without saying that we need this. It was introduced by David and Sams in their 2 works like Asterisk and the monograph. And probably you have seen it so many times so far, but let me just state it. That a set E is uniformly n-rectifiable if it is an Alphorst-David regular and if it has big pieces of Lipschitz images. So this condition says that we have big pieces of Lipschitz images. There are several equivalent definitions. For example, if omega is a two-sided corkscrew domain and it has like Alphorst regular boundary, then the boundary is uniform rectifiable. And if omega, in particular, if omega is a chord-arc domain, then apparently the boundary is uniform rectifiable. This is actually showed by David and Jason, or well, even more by David and Sams before. And in order to state our theorems, we also need to introduce the sets of finite perimeter. Okay, so we say that an open set omega has finite perimeter if there exists an Rn+1 valued radon measure mi sub omega in Rn+1, such that all the variation is finite. And of course, we have this integration by far formula, which is like a Green's formula. And this is necessary, as you can understand, because like in boundary value problems, we want to be able to integrate by parts. So we definitely need something like that allows us to do this. So in particular, this omega, this mi sub omega, is the gradient of the characteristic function of omega in the session of distributions, of course. Now, we would like to introduce also the notion of reduced boundary. And it is exactly the set of points in the support of mi omega such that this limit exists and belongs to the unit sphere. So, and this is exactly what we call outer measure theoretic normal, unit normal to omega. And one can show that in particular, mi sub omega is exactly ni times the n-Hausdorff measure on the reduced boundary. Okay. So with this notion now, we have a Gauss-Green theorem on sets of finite perimeter, this Gauss-Green theorem, but notice that we integrate over just the reduced boundary. Well, this is not always good enough. Apparently for us, we need the full boundary. So we assume, and we put this assumption, so that in fact, the reduced boundary exhausts almost all the topological boundary up to a set of Hausdorff measure 0. So in fact, we can integrate by parts on the boundary. Okay, so for example, if omega is bounded and its boundary is n alpha Ravid regular, then omega has finite perimeter. And also, if we have a two-sided corkscrew domain, then this condition that we ask is satisfied. So it's not an unnatural condition to ask. All right, great. So now let us go to the solvability of the regularity problem in LP. What is the history, in fact? So in 1978, in C1 domains, Fabes, Jodate, and Riviere showed that the regularity and the Neumann problems are solvable in LP for any P, of course, between 1 and infinity. And in fact, they did it using like layer potentials and proving compactness, in fact, of the boundary, on the boundary. So, but then, so they used the Fredholm theory, but this was not applicable then. If you will go to domains beyond C1, so in fact, Lipschitz domains, for example, as Fabes, Jodate, and Lewis showed. And so in 1981, in Lipschitz domains, Jerison and Kenig proved an L2 solvability using this Rellich inequality, which is very important, in fact. Like this inequality is very important. And in fact, later in 1984, Verkota showed the LP solvability and the regularity problem from P between 1 and 2, to include it, of course, by showing invertibility of the single layer potentials. And in fact, he also used this Rellich inequality. And then in 1987, Dahlberg and Kenig also showed like the LP solvability using a different method of the regularity problem between P between 1 and 2 plus epsilon. They also showed invertibility of layer potentials at the endpoint space as well. So Hardy spaces, BMO spaces. But apparently this paper was very important because they also showed the Neumann solvability. So I will just, but definitely I will not mention anything about Neumann as much as I can. And then in the same paper that I mentioned before for the Dirichlet problem, Hoffman, Mitrea, and Taylor also showed that for a fixed P, there exists an epsilon such that for all epsilon regular Semskenic Toro domains, the regularity problem in LP is solvable. All right. This is the history. And then there was a question posed by Kenig already in the conference in 1991, asking the following: if omega is a chord-arc domain with connected boundary, is there a P for which the regularity, okay, Kenig also asked if the Neumann as well, is solvable? And then he also asked, are the layer potentials invertible in LP as well? So those were really important questions. And in more general domains than Lipschitz, apart from Hoffman and Mitrea Taylor, there was pretty much nothing. Although there were a lot of things that were done in the Dirichlet case. So, okay, and then let us recall again what the regularity problem is. So we say that the regularity problem is solvable in LP for the Laplacian if for any f, which is a Lipschitz function of the boundary, the solution of the continuous Dirichlet problem with boundary data f satisfies exactly this non-tangential estimate. Remark. So first, one may fail if the boundary is not connected. So it's really easy to see that with this example that I have stated there. And also with Xavi in our paper, we construct a chord-arc domains in dimensions R4 and higher that they have connected boundaries and they still, like one still fails. So this means that somehow, in order to solve the regularity problem in such domains, we need a different Sobolev space, a more general Sobolev space. And this Sobolev space is the Hausdorff Sobolev space. I don't know if you're familiar, but let me just introduce it. So first, for, let's say, Borel function f, the boundary, we say that G is a Hausdorff upper gradient of f if G is positive, not negative, and it satisfies this condition here, f of x minus f of y is less than or equal to x minus y times g of x plus g of y for almost all x and y on the boundary. Okay, and then let's denote the collection of all the Hausdorff upper gradients by d of f. And then we define the semi-norm W1P of f to be the infimum over all the Hausdorff upper gradients of f of the LP norm of G. And then the norm, we just add the LP norm of f. Now, and we can just define by the gradient, the Hausdorff gradient, let's say, to be the function G that infimizes the above norm. All right, so we will use this now. So the main result is the following. We say that we start with an omega, which is a boundary domain. Then we assume that it is a corkscrew domain, so it has interior corkscrews, as we said. We have that the boundary is uniformly rectifiable. We assume that the reduced boundary exhausts almost all the topological boundary. And then we prove the following. If the Dirichlet problem is solvable for P prime, right? So which is the Helder conjugate of P, then the regularity problem with boundary data in LP is solvable in this sense. So the non-tangential now estimate is bounded by, we have that the LP norm of the non-tangential maximal function of the gradient of U is bounded by C times the Sobolev norm of F, actually the semi-norm, in fact, for any F ellipsis on the boundary. So this is the main result. So this gives a positive answer to the question of Kenig. In fact, to be fair, we prove way more, but I cannot really discuss them now. So a corollary is just that if you have a bounded chord-arc domain, then the regularity problem is solvable. So this is just an easy consequence. And then if you have a two-sided chord-arc domain, which means that both omega is a chord-arc and the exterior is a chord-arc domain as well, then we have just the usual tangential derivative on the right. And that's it. So, all right. Very good. Let me try to explain now the strategy of the proof. So, Steve, what time is it? You have 45 minutes. 25. Okay, I think that I went way too fast. All right. So, in this case, let me go a little bit slower here, so that we can understand what was going on. So, the main estimate we are after is the so-called one-sided Rellich inequality. So, and it is this. So you see, like, we want to bound the LP norm of the normal derivative of U, which is U is the solution of the Dirichlet problem, of the continuous Dirichlet problem with data F, by what? By the Sobolev semi-norm of F. So this is what we are after. If you recall now, like, I mean, let me go like a little bit back since I have plenty of time and remind you this thing that I was saying. So you see, like, here that Jason and Kenig prove this Rellich inequality. So you see, they have both sides. In fact, having both sides gives you also the Neumann problem. So you see, like, the one side from left to right will give you the regularity problem, and from right to left will give you the Neumann problem. But in any case, you see, this is a very, very important inequality. And now let's go back to what we were doing. All right. So we are after this inequality. So let me show you and convince you that this is enough in order to prove the regularity problem. So the reduction is just like how are we going to bound now the non-tangential maximal function of the gradient by this Sobolev semi-norm? Well, what you do is, in fact, just essentially integration by parts. So you just use that U by simple integration by parts, in fact, well, in regular domains, let's say, is written as the double layer potential. So this is the two operators, the double layer of the trace of U at the boundary minus the single layer of the normal derivative of the boundary. And the double layer is the first operator, and the single layer is the second operator, and E is nothing but the fundamental solution for the Laplacian. So those two operators are very, very important, in fact. And when I was saying we invert layer potentials, actually, these are the layer potentials we invert. It's just that for the regularity problem, the Dirichlet problem, the natural, let's say, layer potential to invert is the single layer. While if you manage to invert the double layer, which is a lot harder, in fact, in particular, will give you also the Neumann problem, and that will be very nice. So, all right, but let's forget about this. Let's focus now on this identity. So if we integrate by parts, as you see, and use like Green's formula, in fact, what we do is like we bound the gradient of U of F by just like the non-tangential maximal function of the gradient of the double layer plus the gradient of the single layer. And now, okay, so notice that the gradient of the single layer is nothing but the Riesz transform. And we know, in fact, by the work of David and Sams and the work of Nazarov, Tolsa, and Wolberg, that this is the L2 boundaries, for example, or the LP boundaries, is equivalent to, or is equivalent to uniform rectifiability. So by a Cotlar's inequality, we can show that, in fact, the second bound is true. So the non-tangential maximum function of the Riesz transform of the normal derivative is bounded by the OP norm of the normal derivative. And then for the first one now, the first one is more delicate, and it comes from the paper of Hoffman, Mitrea, and Taylor. And for this, they needed to, in fact, define some particular Sobolev functions that work very well with integration by parts. And eventually, one of the things we did in the paper is for Lipschitz function to identify these derivatives that Hoffman, and Taylor used to the tangential derivatives. So exactly the tangential derivatives after minus sign. And now, as you see, we have that the first, like we use now two, so the one side Rellich in order to go to pass to the semi-norm of F, and that's it. Essentially, that's it. Because it's very easy to see that the tangential derivative at the boundary, so the tangential derivative of F is bounded by the Haiwa's semi-norm. So, okay, so in fact, that's how we pass. Now, but this is somehow this is a trick, let's say, that it is well known. Whenever we have boundaries of layer potentials, essentially, this is how we pass from one-sided Rellich to the solvability of the regularity problem. But how do we prove, in fact, the one-sided Rellich? This is the hard part. All right, so let's see. Let me start with like saying what the normal derivative is like, I mean, the weak sense. So if you have a u, which is like in W12, so the usual Sobolev function, that is like its gradient, the gradient of u is in L2 in the whole domain. And so that it is harmonic, we say that G is the normal derivative of u at the boundary, the weak sense, if 3 holds. So you see, we have on the left-hand side that the gradient of u dot with gradient of phi, where phi is a Lipschitz function all the way to the boundary. So it's a Lipschitz function defined in the interior, but also on the boundary as well, and is equal to the integral on the boundary of g times phi restricted on the boundary. So this is what we say like normal derivative in the weak sense. And now our goal, in fact, is what? Our goal is to prove this bound. Like we define the linear functional t sub u of phi on Lipschitz functions as like this bilinear form. And we want to show that, in fact, this bilinear form is bounded up to a multiplicative constant by the Sobolev semi-norm of F times the LP prime norm of phi. Now, once we have this, we just extend it. This extends to a bounded linear functional on LP prime, and then by this representation theorem, you have your function that you were after. So there exists a normal derivative such that this holds. All right. So how do we do this? Well, this is a pretty like delicate argument now. Well, we first take f to be like a Lipschitz function of the boundary, and we solve the continuous Dirichlet problem. This is the first thing. So u sub f is the solution. And then for phi being just like the trace, like the restriction of phi on the boundary, which is Lipschitz, we solve now the Dirichlet problem in LP prime. So this is W phi, our solution of the Dirichlet problem in LP prime. It is denoted by W sub phi. All right, very good. So finally now, what we will do is like we will consider another extension, not a harmonic extension, another extension of f of the first data, so of the Lipschitz data that we solve the continuous Dirichlet problem for, so it is an extension of f, and it is continuous all the way the boundary, and it is in the W12 space. And then it is well known that the solution, the u sub f and the w sub phi are also energy solutions. So they are also W1, 2. And of course, like they're continuous all the way the boundary because the data are continuous. And thus, we have that the phi minus w phi is a test function. And then the u sub f minus v is also a test function. So what we're gonna do now is essentially, we will start like removing things from or chasing things in the bilinear form. So we start with our initial bilinear form, and then we add and subtract like the solution of the LP prime Dirichlet problem with bounded data phi. So because u sub f is harmonic, then the first, and phi minus w phi is a test function, the first goes away. And then again, we add and subtract now the extension that I told you. So, and then because w phi is harmonic, then this goes away as well. And essentially, we are left with the bilinear form, which is grad v, which is the extension, dotted with grad w phi, which is a solution of the LP prime Dirichlet problem. And now, essentially, what you would expect is like, to just integrate by parts, pick up the Laplace of v, which, as I said, is not harmonic, times w phi, and then the boundary terms. But okay, this is not exactly possible, but we do something which is as good for us. So what we will do is like, in fact, we construct an extension v that they satisfy this upper bound. So you see, like essentially, this is more than enough for us, because the second part is exactly the desired part, and the first part is exactly the hard part. So somehow we would like to be able to construct an extension so that, okay, recall that this is true, to construct an extension so that this inequality holds. So we know that the non-tangential maximal function of the solution of the Dirichlet problem is bounded in LP prime norm by theta, the LP prime norm of phi. So we would like a cool function space so that, this will give what we are after. Essentially, this will give the desired part that we have. And this reminds us of the Carlson embedding, right? The traditional Carlson embedding. But it's not quite that. We need like a better version, let's say. Now, what do we need? So what we need is a suitable version of Carlson embedding, so that actually sees the LP prime, so norm of the non-tangential maximal function. So what we do is, in fact, we define the Carlson functional. So if eta is a sign measure in omega and x is a point at the boundary, we just denote the Carlson functional as you see. And then, okay, if G is in L1 log, then we just set it as we expect as an integral. And then if you have like a non-negative radial measure mean in omega, this is called Carlson when exactly we have the essential supremum on the boundary, this Carlson functional at x is bounded by a constant state. This is an L infinity version. But for us, the required version is an LP version. So we need an LP version of the Carlson embedding theorem. And so what we show is that this hard term essentially is bounded by a constant multiple of the non-tangential maximum function of W phi, which is the solution of the Dirichlet, LP prime Dirichlet problem with bounded data F, times the Harder-Lego maximum function with respect to the surface measure of the Carlson functional of the Laplace of V. And then apparently we have boundness. So apparently it is enough to bound the LP norm of the Carlson functional of the Laplace of V. And that is what we are doing. So Steve, how much time do you have? Oh. So, okay, so what we are after is, in fact, we start with an Lipschitz function of the boundary, and we construct an extension that satisfies somehow we need to be able to bound. So we construct an extension which is an energy function. It is continuous all the way to the boundary. It is exactly phi on the boundary, and it has this quantitative estimate. So the LP norm of the Carlson functional of the Laplace of V is bounded by a constant multiple of the semi-norm of the Hausdorff semi-norm of F, W1P, of course. And to construct such an extension, in fact, we use the following ingredients. So, okay. So we first need an auxiliary extension to omega, which is based on the Doronsoro coefficients that they concern like the best affine approximation of Sobolev functions. Then we need a geometric result, which is like a delicate corona decomposition of omega in terms of bounded star-like Lipschitz subdomains and some buffer regions that they are small, meaning that essentially, you know, we can, the cubes associated to them, they have Carlson packing. And then the last fact that we use is like that the regularity problem is solvable in bounded star-like Lipschitz subdomains for any p between 1 and 2 plus epsilon with uniform constants, right? I mean, this is important because the constants depend just like they're uniform and they depend only on the Lipschitz character. And then the corona decomposition, like the subdomains that we construct, they have uniform Lipschitz character. This is very, very important. So, all right, let us maybe remind, maybe show you for the first time. So the construction of the auxiliary extension. So, all right, given a ball B in Rn plus 1, center of the boundary, and an affine map A, we consider this coefficient, which is the gamma coefficients. And now, some of you may recognize like the omega coefficients of Doronsoro, and this is like the second term. So it measures like how well a Sobolev function is approximated by affine functions in the scale invariant way. And then, but then we also need another coefficient, so another term, which is like we just take the gradient of A. And then we take this infimum over all possible affine maps. And now this idea goes back to another paper that I have with Jonas Azam and Michele Villa, but it is about Doronsoro on uniform rectifiable sets that Michele will talk this week. But this is more delicate. Like, I mean, the other one is a lot more delicate. But in any case, what we do is like, I mean, we take A sub B to be the minimizer, and then essentially we extend somehow, let's say, the Whitney extension type. It isn't a Whitney extension type argument. But what you do is like, I mean, you take a partition of unity subordinate to a Whitney decomposition of omega, and then what you do is you sum over the Whitney cubes and then you have phi sub p, which is like the partition of unity, times A sub p, which is exactly the infimizing affine map. And then for the boundary, you just write f is equal to the capital F is equal to f. And then what we showed with Xavi is like, in fact, that this particular extension is Lipschitz all the way to the boundary, and the Lipschitz constant is bounded by constant multiple of the Lipschitz constant of f on the boundary. And this is important for our arguments. And then, okay, so eventually what we do is like, okay, I wrote that for experts, we have like a union of the bounded Lipschitz star-like domains. Omega sub r is just like all the top qs of the corona decomposition, and then we have this buffer region. But you know, for non-experts, in order like not to worry too much, just like consider like a family of a canonical family of domains. And then what happens is, like as I said, omega j is star-like Lipschitz domain. Then they are also, their boundaries are disjoint. And then almost every x of the boundary belongs to a unique omega j. And then the final step is what we do. So we have constructed this, this extension, but this extension is not exactly, this is auxiliary. So it will be good in the buffer regions and at the boundary. But then what we will do is that we will use the solvability of the regularity problem for this particular P in each subdomain. And then we will solve it with boundary data, exactly F restricted to the boundary of the domains. So this will be our data. And this data is Lipschitz. And this is important. So then we pick up exactly, this quantitative estimate. And the desired extension is, as I said, it is going to be the solution of the Dirichlet problem in each subdomain. And then in just in H, it's going to be the auxiliary extension. And then, of course, you can see that this satisfies the desired properties. Well, you can see, I mean, it requires some work. And I just wanted to show you what is this almost harmonic extension. So what you will pick up eventually is like the Laplace of V is exactly the sum over, or let's say the top cubes, so of the normal derivative of F minus the normal derivative of U, which is like the solution of the regularity problem, times like the Hausdorff measure just on the part of the boundary, which is inside the domain, plus the characteristic function of eta, so on the buffer regions, times delta of Laplace of F. And then exactly because of this, the fact that the buffer regions are small, and we have this quantitative estimate, and we have this particular auxiliary extension that has very good estimates, we are able to manipulate things and eventually get this estimate that we wanted. And I think this is where I want to stop.